Part two then of the step two calculus module booklet. We're going to do these two questions here. So yeah, let's just get straight into it. Going to get some marks for differentiating these things. For differentiating a log, we just put this thing on the denominator and then differentiate this thing and put it in the numerator, which will look like this, because of course this is the power of a half. Bring the half down, times by the derivative of the inside, which is 2x, and then lower the power down by 1. Some stuff cancels here. It also says simplify your answers. I decided the first thing to do would be to times this top and bottom by x minus this object here, because then I'm sort of kind of rationalizing it almost, because you get an x squared, the middle terms will cancel, and then this is 3 plus x squared, except they're negative, which is great, because that means the x squareds go away. Now the numerators also do something nice. It's not as nice, but you get 1x here, and the last two terms, because the half and the 2 cancel, and then this and this cancel, also give you a minus x. So those two things cancel as well, which leaves you with something that looks a bit like this. And then you could times top and bottom by 3 plus x squared to the power of a half, which will give you something like this. Of course, you just introduce it in the denominator, it would go away here, and then this would round up to a 1. And then this and this cancel, the minus 3 and the minus 3 cancel, and you end up with something relatively simple, which just looks like this. So a bit of playing around is required to get there, but yeah, a bit of simplifying and you get down to there. This one's just product rule, of course, differentiate x for a 1, leave this alone, and then differentiate this in the same way we just saw, and leave the x alone, and you end up with the 2.5 cancelling again, but with an x squared outside. You can imagine this is all over 1, and then times by 3 plus x squared to the half again, and you get something like this, because those two terms come from just this one, rounding up to a power 1, and then this just cancels out when you times it by 3 plus x squared to the half. So you're just left with the x squared from here, which is that one, and then of course the denominator has it in there now. So you end up with something like this, and that's about as simple as I'm going to get it. Cool. Hence find the integral of that object there. How on earth are you going to do that? And how are you going to use these two results to help you with that? Well, let's just think about what happens when we add these two results together and differentiate. What we've just shown is that if we differentiate these two things either together, we're going to get this plus this, which is this, which isn't very helpful. However, it's almost helpful, because what if this here was just a 6? Because if this was just a 6, then you could factorize out 2, and you'd end up with 3 plus x squared to the power 1, which would cancel with this, and you'd have 3 plus x squared to the power of a half, which is this integral that you're looking for. So that would be amazing. How do you make that a 6? Well, you just make this a 3, I guess. So instead of differentiating this plus this, you differentiate 3 lots of this plus this. And then it all works beautifully. Factorize it out, cancel it down, and you end up with the derivative of this thing is this thing, which is perfect. Divide both sides by 2, and then if you integrate both sides, of course, the integral over a derivative is just the function itself, and the integral of that is what we're being asked to find. So the integral of that is just a half of that thing that we had there. And we're all good to go. Part 2, find the two solutions of this. Now, this is not a second order differential equation, because it's not d2y by dx squared. dy by dx all squared is a very different thing. So this isn't a second order differential equation. It's also not a first order differential equation that you would have really seen before, because it's actually a quadratic equation. It's something squared plus some amount of the thing, and then a constant, and then equals 0, I guess you could write. Right? So this is actually a quadratic equation in dy by dx. So what do you know about quadratic equations? Well, you could factorize it, I guess, or at least you could try, but not all quadratics factorize. So maybe you just want to skip that entirely, and instead just use the quadratic formula, which you should know does just always work on quadratics. So because this is a quadratic built out of dy by dx, you can use the quadratic formula just equals to dy by dx. I actually made a video about flexing on maths where I did this, but it's nice to see it actually have a useful purpose and actually work in a question. But yeah, b is just 2x, a is 3, c is minus 1, you put it all in, and then you see this object, which is beautiful, because if you factorize out 4 and root it down to a 2, you can cancel it down and end up with an x squared. This should be an x squared, sorry. Does it turn up later? Okay, sorry. This should be an x squared because of this x squared there. That should be an x squared. And then what I'm saying here is that if I integrate, of course, both sides, integrate dy by dx for y, but if I integrate this side, and that's pretending this is an x squared here, then I can use this result, because I can just integrate that and I can do a third of this answer, right? So that should be an x squared. X squared plus 3 is the same as 3 plus x squared, of course. Root of that is the same as power of a half. So this over 3 is just the integral of this over 6. So apologies for not writing the x squareds there. Anyway, I also need a plus c because I noticed they're going to ask me to put y equals 0 and x equals 1 in. So I'm going to do that. I'm going to put in y equals 0, x equals 1. All this simplifies down relatively simply to be this. When you bring a plus minus to the other side, it's going to become a minus plus. And then I can write both solutions out, I think, like this. And I think that's just about okay. And we'll be done, I think, with that whole question, which is kind of exciting. Quite a nice question. Anyway, the next one is a differential equation via a substitution. If you want to practice more of this, there's plenty of it in the it's the FP1 Excel book. I think there's a chapter on this in it. So do have a look at that if you have access to that book. Anyway, differentiate dy by dx here to get product rule, right? So du by dx and then leave this one alone, and then u, and then differentiate this for a half, and then 2x cancels to just make x, and you end up with this thing here, bring the half down to a minus half. Good, so that's that. 1 over y is obviously just 1 over this. So let's just put 1 over y there, and then dy by dx, just put it all in there. And then this y can also become the thing that they want us to be y. So this here is just 1 over y from here. This is dy by dx, we just worked it out. And this y is here. And what we notice goes really well here, if we times everything by u, is that when we expand this out, this will cancel with that, which is great. So this just ends up being a du by dx. And then this doesn't cancel with this because this is already on the bottom. So it just becomes an xu over 1 plus x squared, or 1 plus x squared to the minus 1. U goes over here, u goes over here because you times by this u both sides. But this thing here and this thing here are actually just the same thing, which is amazing because now we just get to here. This is just a separable first order differential equation. So you just divide by u squared, put the dx over here, integrate both sides, and you end up with this here, which is fantastic. This integrates super easily, of course, because it's f dashed of x. It's just a reverse chain rule, right? Times f, yeah, it's just reverse chain rule. So we get this here. We can write u minus 1, or we can write u as this over this, I guess, which means u minus 1 is this thing flipped over, which is here. And then I think I just put in 1 and 0 at this point, or did I try doing some simplifying? Oh, I did some simplifying first, I guess. So I divided everything by this thing to get there. And then I put in 1 and 0, which gave me c was this, because this all just goes away, and you just get 1 minus a third. So we get this, and then we can put that all over 3, I guess. Oh, I times by minus 1 to put this here and this here. I'm just doing basic algebra stuff at this point. It's not very complicated. Put the whole thing over 3, I guess, then flip the whole thing over, and we end up with this here. And that will be our answer to the first part. So yeah, cool. Next part, find the solution to this. Now, what they're asking us to do here is solve a very similar looking differential equation. All they've done is replace x with x squared a couple of times, or increased, I should actually say, sorry, they've increased the power of x by 1. And they're not giving us the substitution to use. So we need to look at the substitution and go, okay, well, the obvious thing to do, because they've increased the power of x by 1 each time, is just to increase our power of x. So let's try that. Now, the other thing we need to do before we continue, just to check that this might be the right idea, is to really study our first question and think, well, what went really well about that? And the bit that went really, really well was that this term here, if you remember, cancelled perfectly with this term here. And so all we had was just a separable first order differential equation. So that's the bit I'm going to look out for when I do this, is I'm wanting this to cancel with this. If it doesn't, I'm going to have to think of some way of making it. So okay, let's do dy by dx. Let's do u by x, just product rule again. Yeah, it's just, okay, sure, great, just product rule, easy. And then we put in 1 over y, which is 1 over this, and then times it by this whole object here. So this is the 1 over y. This is the dy by dx there. And then I've put in x squared y, which is here, and then just the thing that they've got at the end there. And now I look at this and I think, okay, well, this hasn't worked that well. Because when I times everything by u, a u does go here, and this thing here and this thing here do combine to make a 1 over x cubed, 1 plus x cubed on the bottom. But this 3 over 2 messes us up, right? Because it means that this term here no longer cancels with this because there's only 1 of them there, whereas there are 3 over 2 of the terms here. So this hasn't worked, right? So we're going to need to think of some way, essentially, of getting rid of this 3 over 2. Now, the 1 plus x cubed idea does seem like the right idea, because of course I'm still going to need this bit here to cancel with this bit here when it combines together. So that seems fine. You could think about just putting a constant in front of this somehow, or in front of this somehow. The other thing you could think about doing, of course, where you can introduce a term in the front of this, remember this is from the derivative of this term here, because this is the product rule, it's derived from here, so this 3 over 2 comes from the derivative of this guy here. So to maybe bring that down a bit, you could replace this half with a 1/3. And actually, you'll see that that works quite well, because the 1/3 that brings down when you differentiate cancels perfectly with this 3 that comes out when you differentiate. And you end up with one of them. So that's beautiful. So, okay, we've got the exact constant we need. Does everything else still cancel in the correct way? Well, here's the 1 over y. There's the dy by dx that I've just put in there. And we can see, yeah, times everything by u. And then this thing doesn't cancel with this thing, but combines together to make a 1 plus x cubed on the bottom. It does cancel with this thing still, so that's fantastic. And so, yeah, we're perfect. This thing here is going to cancel with this term here. And we'll just end up with this right here. This u squared comes from times by u. And yeah, again, simple. It's just a simple separable differential equation. We're going to put this over here, this over here. This integrates perfectly because it's just reverse chain rule again. We get to this. 4/3 times a quarter is a third, times this 3 makes 1. So we get an x squared there, so that's fantastic. And we just do the same thing that we sort of did before now, right? So u is y over this thing here, which means u minus 1 is this over y. So I'm just going to put that there maybe. At this point, I'm just going to do some simple math stuff, I guess. Divide by this to the power a third, I guess, to get to here. Put in y equals 1, x equals 0, I guess I'm going to do at this point. Minus 1 minus a quarter is minus 5/4. So we get to here. You can write the whole thing over 4, I guess. But before flipping it over, times everything by minus 1. And we end up with this whole thing here, I guess. So we're done there. Fantastic. And then we'll put those two things next to each other like this. And then we'll say, okay, give without proof a conjecture for the solutions of this. So basically, this case had n equals 3 in it, and started with a 4, had a 5 there, and then 3's everywhere else. And this one had an n equals 2 in it, essentially. Had a 3, a 4, and then 2's everywhere else. So when you put an n here, I think it's going to have an n plus 1 at the top, an n plus 2 down here, and then just n's everywhere else. And I think that's the suggestion, without any proof, because I don't need to give any, it hasn't asked me to. And I think that'll be the whole question done. Thank you for watching, and I'll see you next time.